Hello, my name is Kalpana Barnes and I'm a manager of cell imaging applications at SARTORIUS. Today I will be discussing and walking you through a poster previously presented at the April 2022 American Association for Cancer Research, titled Label-Free Real-Time Live Cell Assays for 3D Organoids Embedded in Matrigel. Since organoids display structural, morphogenic and functional properties that recapitulate in vivo physiology and pathophysiology, they are increasingly being used in vitro to model organogenesis and offer platforms for drug discovery, disease modeling, personalized and regenerative medicine. To use these models across a range of such research areas, technologies used to not only image but also quantify phenotypic responses in these complex 3D structures are key. In this poster, simplistic and robust workflows are described for monitoring and quantifying organoid parameters in a non-perturbing manner. This is achieved using the IncuCyte live cell analysis system and integrated analysis software to kinetically visualize and quantify organoid size, number, and morphological features. We present validation data characterizing the differentiation and maturation of organoid cultures in both 24 and 48 well plates. And in 96 well plates, use integrated label-free metrics to assess the effects of treatments on organoid growth, study and reveal compound mechanism of action, and in a disease setting, assess CFTR function. The IncuCyte live cell analysis system itself is a fully automated phase contrast and multicolor fluorescence system that resides within a standard cell culture incubator for optimal cell viability. The instrument is designed to repeatedly capture images from a wide range of flasks and plates over time. Integrated IncuCyte software provides rapid and flexible control for continuous live cell analysis, comprising image acquisition, process, and data visualization. In addition, a collection of non-perturbing cell labeling and reporter reagents suitable for live cell analysis are available. To start, here we show schematics describing IncuCyte validated protocols for either culturing or performing 96-well assays using organoids embedded in Matrigel. For culturing, organoids are harvested and the cell pellet resuspended in Matrigel. The Matrigel suspension containing single cells or organoid fragments is added to either 24 or 48 well warmed microtiter plates as droplets of 10 microliters to 48 well plates or 30 to 50 microliters to 24 well plates. After incubation at 37 degrees to polymerize the Matrigel, these droplets appear as domes. To assist IncuCyte imaging of the whole dome, the suspension is spotted centrally within the plate. Cell type specific media is added over the solidified dome, and organoid formation and growth monitored within the IncuCyte, which captures repeated 4x bright field images. For assay, the organoid Matrigel suspension is now seeded into 96 well plates using one of 3 validated formats, either as 10 microliter droplets or domes like the culture setting described, or as a 50 microliter suspension added directly to the assay plate. A third option, where 50 microliter suspension is added on top of a layer of pre-polymerized Matrigel. The choice to format is dictated by the health of the cultures and organoid morphology as visualized in the culture phase of the organoid workflow. The IncuCyte automated image acquisition and analysis tools can be used to remotely monitor the development of your cultures, providing a setup and walk-away experience. Displayed, a 24-well microplate vessel view of hepatic organoids in Matrigel domes. The vessel view function enables rapid and simultaneous visualization of images from all wells, and a zoom-in function allows closer interrogation of images and wells. Identification and segmentation of organoids in each dome across the seeding density titration is shown in yellow. The IncuCyte's real-time automated microplate vessel view and time course plots demonstrate that organoid growth rate and size is proportional to cell number. Here we exemplify the IncuCyte's ability to monitor and quantify growth in Matrigel domes across a range of organoid cell types. Mouse intestinal, pancreatic, and hepatic organoids were embedded in Matrigel domes in 24 well plates and imaged every 6 hours. Organoid differentiation, maturation, and growth was measured in real time using the IncuCyte's automated organoid software analysis module, which tracks changes in organoid size or their area over time. In the top panel, you see the software is able to capture, as a single 2D in-focus 4x image, individual organoids embedded throughout the entire Matrigel dome. Zoomed-in bright field images on the bottom panel and time courses reveal cell type-specific morphological features and growth profiles, respectively. Note the accurate segmentation as shown by the yellow outline mask of the different organoid morphologies, and the comparable rapid growth and larger size of the mature hepatic and pancreatic organoids compared to the slower growing, smaller intestinal organoids, which display a characteristic budding morphology as they mature. To assess the impact of treatments on organoid growth and morphology, mouse intestinal and hepatic organoid fragments were embedded in Matrigel in 96 well plates and allowed to form organoids for 3 days prior to treatment with the protein kinase inhibitor staurosporin. Changes in organoid size, number, and shape were kinetically monitored and quantified over a 4 to 10-day period. Bright field images and corresponding time courses of bright field area in panel A reveal the continued growth of vehicle-treated organoids and the inhibitory effects of staurosporin across both cell types. Enlarged images in panel B show staurosporin-treated hepatic organoids lose their rounded phenotype and darken. This can be quantified over time using IncuCyte's eccentricity and darkness metrics, where eccentricity describes how round or compact objects are, and values range from 0 to 1, with the perfect circle having a value of 0. The darkness metric describes the average of the darkness of the bright field objects in the image and ranges from 0 to 100, with the darkest objects having a value of 100. Time course plots show staurosporin caused a marked reduction in the number of organoids and induced a time-dependent and parallel increase in the eccentricity and darkness, which align with the loss of the round phenotype and cell death images that were being captured. As patient-derived organoids preserve the morphological and molecular characteristics of the tissue or tumour of origin, they are increasingly being used in vitro for drug development models. The ability to perform multiparametric quantitative measurements and distinguish between cytotoxic and cytostatic cellular responses is important to establishing effective anti-cancer therapies. To exemplify drug-specific changes in organoids, hepatic fragments embedded in Matrigel were allowed to form organoids for 3 days prior to treatment with known chemotherapeutic agents. Bright field images captured 2 days post-treatment show compound-specific effects on organoid size in terms of their area and morphology with respect to their roundness, that is, eccentricity, and darkness. The representative images and concentration response curves constructed from the area under curve analysis of the size, eccentricity, and darkness time courses demonstrate a difference in profiles between cytotoxic and cytostatic compounds. Cytotoxic agents, staurosporin, shown in pink, and cisplatin in teal, attenuate organoid growth in a concentration-dependent manner, inhibiting organoid area. They compromise and break down the uniformly rounded organoid morphology, reported as a concentration-dependent increase in the eccentricity metric, and cause a concentration-dependent increase in the darkness metrics as the organoids die. 5-FU in black, while more potent at inhibiting organoid growth, can be described as cytostatic, since having little or no effect on organoid morphology or inducing cell death as reported via the eccentricity and darkness metrics respectively. In combination, these three label-free metrics can be effectively used to probe and classify compound mechanisms of action. Cystic fibrosis transmembrane conductor receptor, CFTR, patient-derived organoids are being used to aid functional studies, drug development, and personalized medicine strategies in CF patients. Reports show increases in cyclic AMP levels cause rapid swelling of intestinal organoids by opening the CFTR, and that this response is lost in organoids derived from CF patients. Here we demonstrate a label-free, non-fluorescent-based approach to kinetically visualize and quantify CFTR function. Mouse intestinal organoids formed for 3 days were treated with forskolin and imaged every 15 to 20 minutes for up to 7 hours. Bright field images show following forskolin treatment, organoids increase in size and exhibit a clear lumen. Forskolin-induced swelling was kinetically quantified as a % change in the bright field area relative to the area at time 0. The bar chart shows exposing organoids to forskolin caused a concentration-dependent increase in their size, with 10 micromolar inducing a 3-fold increase after 7-hour treatment. To demonstrate that forskolin-induced swelling is CFTR dependent and thereby simulating the CF disease state, intestinal organoids were pre-incubated with the CFTR inhibitor 172 for 2 hours. Concentration response curves showed 10 micromolar forskolin induced increases in organoid size were inhibited by approximately 60% with the inhibitor. Label-free metrics described can be used to ensure organoid growth characteristics are maintained over exhausted periods of culture. Under routine culture conditions, organoid morphology and growth are expected to remain consistent across multiple passages. Intestinal organoids cultured in 50% Matrigel domes in 24 well plates were evaluated for growth and differentiation consistency over multiple passages. When maintained at a consistent density, intestinal organoids display comparable measurements of count, area, and eccentricity over passage. The bright field images show maintenance of their distinct budding phenotype across these multiple passages. And the data here illustrates how the IncuCyte live cell analysis approach can be used to support robust and reproducible assessment of long-term organoid expansion. In summary, the IncuCyte live cell analysis system can be used to support and address challenges associated with 3D organoid workflows. IncuCyte validated protocols and software can automatically locate and image organoids embedded in Matrigel. The data described exemplify how label-free real-time metrics can be used to optimize and define culture conditions and regimes with fully kinetic profiles providing additional insight. And in an assay paradigm, multi-parametric analysis of organoid cultures can be used to make objective decisions to better predict therapeutic outcomes. all of which can be achieved within the controlled and physiologically relevant environment of your incubator.